right, well, welcome everyone. I am delighted that everybody has joined us today, and I am really happy to welcome Dr. Catherine Nakalembe to our seminar series. She will be our presenter today. Dr. Nakalembe is an assistant professor at the University of Maryland. She leads NASA Harvest Africa and serves as agriculture and food security thematic lead on NASA's Severe Applied Sciences Team, SERVIR. With expertise in satellite remote sensing and machine learning, she pioneers research and applications to advance agriculture, food security, land use mapping, humanitarian aid, and climate resistance in Africa. She is a recipient of multiple prestigious awards, including the Al Sumait Prize, the 2022 Golden Jubilee Medal, which is Uganda's highest civilian award, the 2020 Africa Food Prize, and the 2019 GEO Individual Excellence Award for her commitment to improving African food security through enhanced Earth observations. So I'm delighted that Catherine is joined us today.
So I'm happy to be here. I think I participated a little bit in the meeting in January. I don't remember if I did a kind of a mini presentation, but I'm happy to be here and to meet everybody and kind of give an overview. I might cover a little bit of my work, but maybe not so much. There's a lot of recorded opportunities if you're really deeply interested in the work that we're doing under the Harvest program. But I wanted to share a little bit about what is possible with remote sensing and AI in terms of agriculture, and then might share a little bit of like what we do specifically and what it kind of hinges on. And then I will kind of end talking about more around the considerations. I think in the grand scheme of things, if we're working on grand challenges, there's some things we have to consider as particularly from a technology perspective, whether what we're developing is applicable, useful, and how it can be sustained to be useful for people beyond ourselves as researchers, but communities that we're trying to serve. So just a little bit of a background. NASA Harvest is NASA's agriculture and food security thematic food security program. It's led by the University of Maryland, and the goal is to enable the advancement of satellite observations to benefit food security. We have a huge team at the University of Maryland. Bob Becker-Chef is the program lead for NASA Harvest, and I lead the Africa work. My work also falls under the umbrella of NASA Severe, which is a joint initiative between USAID and NASA. And the idea of Severe is to make research that's been done, beyond agriculture, including climate, land use, accessible to different organizations globally, including in South America and Asia. Severe has local hubs that work with applied sciences teams to make the tools and the research that they've done applicable in those contexts. So I'm the agriculture food security thematic lead, and my current project in Severe focuses on West Africa. So we have a project ongoing with CSC, which is a research center based out of Senegal. And so I think if you've seen any of my presentation before, you've seen this thematic. I like it because it sort of simplifies what we're trying to achieve. We have satellites collecting data every day. Sometimes some are collecting data sub-daily, so multiple images collected over the same area. And then we have stacks and stacks of data going back till the 70s. If you're looking at rainfall, temperature data, you're going back, in the 80s. And to be able to utilize those data, we have to do a whole bunch of things. One is make it analysis ready. We don't do this. You typically work with analysis ready data. There are other teams that kind of focus on this. And in order to get insights out of it, we need field data. So in order to train a machine learning model to predict something, you need to give it examples. So we need a lot of training data on what crops are growing there, or what is harvested in a particular area in order to be able to predict other things. So with satellite data, we can create cropland maps, crop type maps. We can do yield estimation, but we can also do conditions assessments. So we can assess how conditions are compared to the average or compared to a particular year. We also have the advantage of getting rainfall temperature data from satellites. And in many cases where there's no ground data, it's a critical data set to sort of fill gaps, even though there are obviously issues when you do not have any ground validation for it. And so ultimately what you want is simplified, readily accessible information that a policymaker can use to for example, make decisions about bringing aid. For example, right now in Kenya, there are floods that are ongoing. So you want to estimate the area impacted by the flood and predict where people are, and then figure out how much support will be needed. There's also an extreme drought in Southern Africa. It's affecting Zambia and Malawi particularly. And you want to figure out what is the extent of that damage. So in the end, all this complex information has to be simplified into very simple, very basic, sometimes 2, 3 paragraphs that say, in southern Zambia, X has happened. We need this much support. It needs to be brought to this area. Other policy things, this is, not kind of flipping on the other side where it's not emergency response. We're talking about planning better or implementing policies that can help farmers. So once you know that certain areas don't do well for particular reasons, which could be maybe lack of irrigation infrastructure, might be the basic thing that is required to improve productivity in a particular area. And you can show that over time that this area, soil conditions are fine, temperature is okay, but maybe there's a lack of rainfall at a critical moment in a growing season, then you can determine that in order to improve productivity in this area, we need to invest in irrigation infrastructure. The other thing could be you could have all of those things, but productivity is still low, which could be the type of seeds that people have access to. And so you can make accessible the quality, the kind of seeds that are required to improve productivity in that particular area. You could also talk about, changing crop varieties as an example. So this is kind of an overarching, this is sort of what we want to do. We want to use Earth observations to inform those types of decisions. And we do this through many different things, including improving systems where people can access those data, improving the methods that underlie the data that are in those systems or the data that are the basis of making those decisions. And then you want it to be accessible to people that make decisions. And the only way to do this is through partnerships. This Grand Challenges grant, for example, is a clear example of partnerships. Different people have to do different things in order to be able to move from my perspective, to move from all the data to decisions and then actions. Like I would not be able to, for example, figure out where you would buy food that would have to be brought to a particular region in order to, to improve food security in a particular area. But I would be able to tell you how bad drought is. So you have to do these things across working with different partners. And so we have a lot of partners. And so just a little bit about what the applications are and what you can do with AI and Earth observations. Why it's such a big deal now, and becomes bigger and bigger in the sense that we have a lot of data. We have thousands and thousands of satellites collecting data about our planet. And there's an explosion in methods and applications. There are lots of people doing research in this space. So we can do things that, even though we could do them 10 years ago, right now we can do them so much faster. And we have much more sophisticated approaches to it. We have the cloud, which is what this thing around, where the word new era is kind of supposed to depict. That with cloud computing, Catherine, sitting in Uganda in 2020 during COVID, could create multiple maps for multiple countries. This was not possible without me having to log into our cluster at UMD, and it's not possible for a lot of users that don't have that infrastructure. So we're in a new era where more people are looking at different data sets and finding different insights. And so, and while, AI and earth observations are really critical for advancing precision agriculture, it is still, far out of reach for many farmers in Sub-Saharan Africa. So majority of what we're able to offer is large-scale synoptic assessments and analyses that can inform policies at a much larger level. But with a little bit of investment and intentional efforts, we can actually make more granular information accessible and package it in a way that is useful for farmers. So the key applications of AI and EO, I say this, my friend doesn't like it, AI, EIO, Hannah, whom we worked with on this particular paper. She does not like it when I say AI, EIO, but I like to say it. So I'm going to kind of talk about these so that it's kind of a little bit clear, like what can we do to, not make up thing, not create the idea in your mind that we have some magic bullets that do, incredible things. So we can create cropland and crop type maps. These are important for agriculture statistics, for yield estimations, conditions assessments. So you need to know where the crops are, what crops are growing, and then you can do a conditions assessment. So you can know that maize in Iringa in Tanzania is above average. Maize productivity or yield in Iringa is 2 tons per hectare. So you need to be able to disaggregate everything from this image that you see in the bottom left panel and separate out what are crops, what are not crops. And then you need to separate out what are the specific crops growing in that particular area. So we want to do this. It is doing cropland is easier because we're able to generate the labels. I can tell from a satellite image that this is crop and this is not crop. It is not easy to do crop type. You need to be able to get a lot of ground data to be able to do it. And while there's been an immense expansion in the availability of data sets, as I mentioned before, we're getting an explosion in terms of products, and there's so many different maps that are being made available. We worked on this paper with Hannah. It's just been accepted in Nature Scientific Data. And within, we were evaluating different maps available for different countries. I think also Tanzania is one of the countries that we evaluated. And you can see clearly that this is the example for Senegal, that different products don't agree. You can see the map on the bottom left, this map here, compared to the one in the top right, they don't agree. And you can see disagreement in red here across these products. And there's so many. The chart that you see on the left is showing examples of all the different maps and the different accuracies across all of them. So some of what we do is try to give ideas to our end users, like what's the best map you can use. This was also kind of a selfish project in the sense that we're trying to determine, do we need to create maps if others are creating maps? Can we have ways of evaluating them that then we could just use what's available for, downstream tasks like conditions assessment? So another thing you can do is yield estimation. So combining remote sensing and machine learning, we're able to leverage, some field sampling. You can also do machine learning with crop simulation models. There's a lot of research that shows that farmer reporting is unreliable, so we don't typically use those data in our pipelines. But what you're trying to predict is crop harvested per unit area. And when you multiply that by the area planted, then you get to production. This is really important for planning everything from export, import, how much extra do we need of a particular crop. And this requires a lot of input data, and I'll explain a little bit about that in the future. And so some of the work that we've done, this is work supporting an agro project, looking at trying to predict regional yield, and it combines all these different data sets. This is an example sort of the workflow as it goes towards trying to predict at the regional level what conditions are, and then turn that into yield maps. This is an example of yield across conditions, yield, and yield anomaly across these countries as part of this food balance sheet work. The other thing you can do is field boundary delineation. So a lot of what I'm showing is possible and does really great in places where we have a lot of data and fields a little bit larger, particularly for this field boundary work. It's a little bit complicated when we're looking at smallholder agriculture because we're limited by the data sets that we have access to. So at 10-meter resolution, in many cases, a place like Rwanda, field boundaries are unclear. But field boundaries are critical for doing area measurements. If you want to do anything like subplot optimization, actually, I'm going to use the next slide to show what I mean by this is you can see in this plot here that is purple. If you had the boundary of this field and looking at trying to figure out a way of optimizing. So let's say you want to know what part of the field doesn't do great and you want to know how much more fertilizer you could put in and try to figure out if you need to put more or less over a long time period, you need to have the boundary. And so doing this within smallholder fields is not easy because we need very high resolution data. But the other complexity is there's a lot of intercropping, which is not really accounted for with remote sensing. So one pixel could easily be, could have 4 or 5 crops in it. And in remote sensing, with the satellite data we have, would only have a single value. So you can do pest and disease detection. This is typically looking at anomalies. So a field should be doing great if everything else is steady. So rainfall, temperature, soil moisture are kind of normal, but it's still a field is still performing below average or biomass is below average, then the cause could be a disease. And so you're trying to look at those anomalies. And this is an example for, I think this is actually a grape field, trying to look at a particular disease impacting grapes. And then the one on the right, bottom right is picture based, trying to detect disease in banana. And this is work, I think, done out of Makerere University. They're trying to use computer vision to do that. And so from all of that, we have a lot of data, we have a lot of models, but there is such a huge gap between all of these things and impact. So just to talk a little bit about our approaches, some of what we're doing, we're trying to create maps, as I kind of mentioned before, to improve what's available and accessible in the African context, at the same time making data sets and our pipelines accessible. So we worked on, we call it Open Map Flow, which is a library for creating maps using machine learning and remote sensing, in this case, deep learning approaches, leveraging what's readily accessible. And we've had some results when we're still developing more and more. And currently we're working on a project trying to do cropland change in a refugee settlement context in northern Uganda as another example. And an example of the utility of this work, this is from 2020. We developed this map for Togo. It was possible because we had access to historical data, had developed a pipeline to be able to work remotely due to COVID, but also come up with a way of validating. And that's sort of what has evolved into this big library that we use for our mapping. We have an entire pipeline beginning from no data to creating a cropland map. Inspired and motivated by this work. So when you're doing cropland, it's easy. As I mentioned before, you can look at multiple satellite images of a particular area in a particular year and know for sure that this is a crop field. You cannot tell when it is, if it is maize versus sorghum versus millet when you're looking at it from satellite data. And so some of what we've been doing is trying to address this gap. The other thing is data sets like yield. Yield data is not readily accessible. A lot of it is collected through farmer recall, through phone calls, through expert assessments. There's some survey data, for example, through this LSMS by the World Bank. However, the utility of it and access to it is very complicated. And in order to support our food balance sheet work, we've worked on this sampling frame for trying to do yield estimation, trying to figure out where to collect yield data across these countries. So the total countries is 6. And in 2023, we were able to do this in Kenya end to end, basically coming from the strata that we created using NDVI as sort of a way of determining productivity differences, whether high, medium, low, high. And then trying to determine what are the best places to create a representative sample of production across of yield across all of Kenya in this case, and we were able to collect some data. The other way we're trying to address this is, this is also the same project, but in this case, we're trying to collect crop type data. And across the whole country, we managed to get, I think it's over 6,000 points within about a few months. So we're trying different things to solve different problems while we're working towards the broader framework of getting the best available information to decision makers. And why this is important is that what's reported by a farmer versus what is actually measured can be very different. As you can see, the self-reported measure, the mean yield is 976 kilograms per, I think this is per hectare, while the self-reported mean that is based off of crop cuts is 13.9 kilograms per hectare, for example. So this is very problematic. These are very, very different numbers for a similar geography. And then showing, differences in what data, what crop is dominant in one place, what place. The one thing to note is that in this particular project, we're focusing on maize and not necessarily collecting data on other crops. So we're also trying to, come up with smart ways of collecting field data. This is our helmet project, trying to collect street level images that we later on convert into what we call crop type labels, so we can create those crop type maps. We have people driving with helmets, with GoPro cameras on helmets or on a car. And as they drive, we take pictures and then later on use those pictures to extract crop type information. For example, you can see, here's an example of what the model is predicting for maize. And then we have to offset, basically move the point from where the motorbike or car was into the field. And this is an example of some of the data that were collected. And this is only from 2020 within like a 2-week period. And so other things that we're doing is obviously working with extension agents all over the place to collect all these different data sets, in addition to a lot of image interpretation. So we work with students, people in ministries to help us basically clean all the data to create all the labels that we need to be able to predict these different crops. I'm not sure what happened there. And then just a little bit about this work that we did with the Ministry of Agriculture to collect data last year on yield. Is a user-centric approach. The idea is that the ministry wants to be able to do this. We have some funding we received from the Gates Foundation to be able to do the data collection. There is something going on with my slides. I feel like they're going back and forth. I'm not sure what's happening. So going back, I guess they're just in the wrong places. The Ministry of Agriculture, with them, we worked to create a sampling frame executed from end to end, working with extension agents across Kenya in 2020. As I mentioned, we collected over 6,000 points. Half of them were just crop type. We missed most of the season due to late planning, but we're able to collect a decent amount of data for trying to predict and estimate yield across the country. This is from, is an example of some of the data that I was talking about. So I'm going to skip over this because I'm not sure what happened here. And kind of talk about some of the training that we do. Capacity building is critical. One is we produce data sets, but they need to be used. So we work not only with extension agents to train and to work with them to collect data, but we work with them through the Ministry of Agriculture. In the top here, this is Jane Kiyoko from the Ministry of Agriculture, with whom we spent a week here at the University of Maryland trying to work out approaches to being able to execute and collect this yield data efficiently, as well as in support of what they're doing. So the Kenya Ministry of Agriculture has an insurance program, and every end of season, they have to do assessments to determine what areas they have to deploy. They have to, not deploy, they have to pay out. And this is a very expensive thing that they have to do. And so the idea is, how can remote sensing help optimize, but as well as for them to look at a much larger area rather than looking at individual plots where they're collecting the yield data. So just a summary of some of the impact from our work in the past: this risk financing project in Uganda, just using vegetation conditions to trigger the mechanism. The Togo example that I gave, supporting that regional food balance sheet it's a regional food balance sheet in East and Southern Africa, working on these crop monitors that are accessible and utilized by the ministries of agriculture. We don't run them after they're implemented. Developing the systems, like global agriculture monitoring system, where anybody can go in and make their own assessments for any place in the world. And then these crop monitors the tile on the bottom right just summarizes the crop monitors, including global, focused on high producing countries. And then we have one for early warning, and that process is adopted at the regional level through IGAD Climate Predictions and Applications Center. And then we have these national crop monitors that are run by national agencies. And a few weeks ago, we were in Naivasha with countries that have operational monitors, basically to regroup through what we call a learning exchange. So I'll talk a little bit about the considerations. This is the last few minutes of my presentation. One is, in order for us to do this, I mentioned this when I talked about partnerships. I think number one is that we have to work across disciplines. So I might be able to analyze satellite data, but as I mentioned, I might not be able to figure out how to resource and find the food aid that's required to relieve a particular community. I might be able to tell that a particular field is not doing great, but I might not be able at all to tell you what disease is impacting it and how you can solve that problem. So in order to get from insights to improving and making information accessible to different stakeholders and users, and to implement actions that can support farmers, we need to be able to work across disciplines. I use this to show that this data collection project that we had on helmets was only successful because we have partners not only at universities, including Sokoine University of Agriculture and this regional university network and Makerere University, but we also had to collaborate with the East Africa Grain Council, the Regional Center for Mapping of Resources for Development, EASA, which is based out of Austria, Radiant Earth Foundation. So there are many people who made it possible for this project to turn out the way it did. Number two is the resource context of stakeholders. So we've made a lot of advancements, and more tools are more readily accessible, particularly with cloud computing. Not everybody requires a computing cluster or a server to be able to access data. However, the cost of internet is still high in a lot of places. And so while we build our systems, we have to make sure that we're accounting for costs related to internet, but as well as, the fact that not everybody has a fully functioning computer that they can just run with things. In addition to using mobile apps that make it possible to collect data in an easy way makes a very big difference. From a remote sensing perspective, labeled data or training data or ground truth data are very limited, particularly in the smallholder context. You need to collect a lot of examples across really, really large landscapes that are very difficult to tread. So unless we address this gap, we can keep producing maps, but there is no way for us to tell you how well our maps are doing because we don't have ground truth. So this needs to be addressed, and addressing it requires a lot of investment in the data collection itself. It also requires working with extension agents, universities that are local, that can make it possible and cost effective to access those data. So number four is that the methods and the approaches and procedures to creating product or making things, of creating products have to be replicable. So while there's a lot of research ongoing, and we're all pretty happy with the move towards open science, a lot of what's been published in the past was not accessible, cannot be reproduced, and so everybody begins from scratch. In order for the work that we do to be successful, in order for us to stand on the shoulders of giants in remote sensing and Earth observations and AI, all methods have to be accessible. And the transparent part here is that there's a lot of I'm going to use the word sensationalization, in the sense that people assume that we have a magic bullet that you can just make things, through a few keyboard strokes, you can get the best possible product possible. But this is not always true. Maps have accuracy problems. They have all sorts of issues that have to be communicated. So transparency is really important. Limitations of methods have to be communicated. Working with stakeholders from the beginning and having meaningful partnerships are really critical. I've already spoken to this at length, and I believe the Grand Challenges team appreciates this absolutely, given the meeting that happened in January. But that everybody's on the same page and we're trying to work towards the same goal, and it's mutually beneficial. And it's not only purely from, to benefit an individual organization's priorities, which could be research, but that it can advance a critical, pain point for a partner who is trying to really understand what's happening on their landscape. Number 7, around decolonizing research methods and practices. This is very common, particularly when data collection is a key component in the pipeline. As you've seen, I've mentioned we work with extension agents, university students, and are collecting a lot of data, and then we end up publishing. We have to, even ourselves, continuously check that we're not extracting information and knowledge, and it's not beneficial, and that is not being co-developed together with our end users, which is why we have a huge investment in terms of time and effort, and within a lot of our projects, we have capacity building that often requires a lot of co-development and developing things that are useful for our partners, at the same time ensure that we leave capacity within those institutions, similar to making sure that methods are reproducible. So all our scripts and code and stuff that we work with are made public. Institutionalizing investments. This to me is perhaps the highest priority, in the sense that, we can experiment, we can pilot many different things. But for as long as the capacity stays within our institution, so in the US or in Europe or in other places, and it's largely implemented through projects, those investments or whatever it is we're doing doesn't actually is often unsustainable. So as soon as the project ends, that's it. This map here was kind of showing, we did a short study with my undergraduate researcher where we're looking at where a project's based, like what is the headquarters of the institution that's leading it, and where is it being implemented. And we can see huge gaps in terms of who is leading it and where is the headquarters. This means that the ideas kind of cultivated outside of the places where the problems that need to be solved are happening. And so there has to be, it goes back to the decolonize point as well, that this has to be addressed, that there have to be resources within the countries or within the institutions that we want to work with, so that they can take what makes the most sense to keep investing in, or that they can design and describe and decide the direction of the work based on their own priorities. And then for going back to a remote sensing perspective, I mentioned doing field boundaries in a lot of African landscapes is really complicated. This shows an example. I believe this is a screenshot from Kenya. The image on the bottom left is a high res image, maybe about 1.5 meter resolution or so. There are a few, it's not collected consistently. You have to pay a high premium to be able to access this data wall to wall. So it's virtually not accessible for the task that we want to do. The one in the middle is 5 meter resolution. This is from Planet. However, you can see, so this might be a little bit cheaper. more accessible in terms of coverage in the places where we're looking. But you can see that the boundaries immediately fade. You can't really see where the fields begin and end. And the one on the bottom, the one on the right is from Sentinel-2. This is 10-meter resolution. This is open access. And as you can see, the boundaries completely almost disappear. So anything to do with optimization, maybe crop type mapping, all those things go out the window when you start to look at trying to create maps for Sub-Saharan Africa. And then this is one of my next to last slide is I've talked about this a lot already when I was talking about transparency, but there are huge limitations in terms of what we can do with the data set, in terms of what we can communicate. People say things like, I can tell you exactly what's happening in your field from my desk. This is probably never true unless you have on-ground sensors, unless you have data coming from the field, unless you have some very sophisticated way of analyzing those data, which is typically in a precision agriculture setting. So for when we're working in a smallholder context, we don't have a lot of that information and we have to be able to communicate it. The other is when we're predicting things like yield, we have to be able to communicate the limitations, the shortcomings of our approach to doing it, which is we're using historically collected data, for example, to predict current conditions. And without any ground information, we are just giving you an indication of how good things are and not necessarily the truth about what's happening in a particular place. So with all of that, what we want to do, at least from my perspective, what I see as important is increasing access to data analytical tools. So partners can also do what they see is the most important through training, through publishing, through partnering on projects. Number two is prioritizing use-inspired research in the sense that if you want to communicate, if you want to make products accessible to smallholder farmers, we need to be able to create a clear pathway to getting from the satellite data to actions that the farmers need to take. So this requires we have to use a whole other lens to be able to get to that. Expanding our training program also goes to the first one, which is having information more readily accessible through MOOCs and stuff like that, so others can do it without us. And then the other is partnerships with universities. I think this is sort of the same thing. It's about cultivating, the points are different, but they're the same. It's like cultivating partnerships so that end users and institutions within the countries where we're working have access to the knowledge, to the information, to the data, to the tools that they're able to work with and do their own work. And I just want to mention contributors to our work, and we have many, many more within our Harvest Hub, as well as in the countries that we work, and in addition to other partners who are part of the NASA Harvest Consortium. And that's it. Thank you.